second by second, whereas at the moment, we obviously just analyze peak points, so every 4 hours, whatever. But with this inertia monitoring kit, we will be able to get that real-time measurement, which obviously helps us understand how close to the cliff edge we are, because the modeling is great, but actually we could be a long way from the cliff edge and push the system harder, or we could have further to go. And by being able to measure in real time is really going to give us that view. It will also prove that when we get the new forms of inertia onto the system, we'll be able to see the impact straight away as to what it's doing. Sorry. So new services and products. As a system operator, we've really just set out our requirements for faster frequency response products. As I said already, the dynamic containment is our newest one of those just over a year ago. We now have 1 gigawatt of 1,000 megawatts of batteries, predominantly providing dynamic containment. So if the frequency drops, then these things will deliver their gigawatt of power within a second onto the system. And then stability pathfinders of phase 1 I spoke about a moment ago. We contracted just 2 years ago, 12 GVA seconds and £320 million over 6 years. So we reckon that saved the consumer about £150 million, because without these phase 1 Pathfinder projects, we would be having to constrain off more wind to create the space to bring on the gas-fired power plant at minimum generation to get that inertia and frequency response. So there's a real strong cost benefit here. So these Pathfinders and stability products, they're a win-win-win because they're lower cost for the consumer and they're zero carbon and enable you to operate a stable grid. Phase 2, we're about to launch the results of that in the next couple of weeks. But I can tell you now that a good proportion of those are grid-forming inverters, and they'll be on our grid system in 2 years' time. And across phase 2, we're going to procure around 12 gigaamps of short circuit in feed and about 6 GVA seconds of inertia. So again, it's allowed us to really tailor and tweak our technical requirements depending on what the network needs are. So we're not setting a single requirement or a single technology. We are determining the need on the system through our analysis and giving that to the market to then deliver the outcome, because it's the outcome as a system operator that I'm really interested in. And then phase 3 will announce the results of that at the end of the summer, and that's much more of a nationwide, just purely for inertia. And again, we're getting a whole mix of technologies coming forward: synchronous condensers with flywheels, grid-forming batteries, et cetera, et cetera. So it's really exciting that this stuff is coming onto the system. The grid code mod then, so once we've done all this work over the last 3 or 4 years, working with the OEMs, having this very clear, defined requirement on the system, we've then been able to create this minimum viable product for what a grid-forming inverter must, as a minimum, do if you want to use it on our network. So this is really taking it away from the Pathfinders and just sort of saying, hey, if you can define a grid-forming inverter that can connect to the grid system and it can meet all these minimum requirements, then there's a good chance that in future market auctions or whatever way that we want to buy these services in the future, you'll be able to participate. So really now is a question that when you're designing your wind farm or your solar farm from scratch, from the drawing board, do you design it with grid forming in mind? What is the price differential, knowing that it's going to open up to you a whole market for the next 20, 25 years that you may or may not wish to participate in? And I think as we need more of this stuff to drive down the cost of the grid forming inverter technology, and then it'll become much more routine and run-of-the-mill. The other thing we're doing as well is short circuit in-feed. Again, we talk about inertia. We talked a lot about inertia this afternoon, but actually another key component is that short circuit in-feed. We need that to ensure the protection systems work on the transmission system. We need it to make sure the control systems work on the wind farms, etc. It has been an ill-defined measure, certainly in GB up until now. What we're trying to do is make sure that we can tell the developers, look, you're going to be guaranteed a minimum short circuit in-feed. So when you're designing your wind farm controllers, just design it so you can always deal with 2 GVA or whatever it might be at the connection point. And then we then, through our Pathfinders and our market approaches, we can then ensure we procure through these services enough short circuit in-feed such that we can guarantee those levels. Then I expect over time that the short circuit in-feed requirements will also then find its way into the codes and the frameworks as we manage and design the network. And short circuit in-feed will come very much like a voltage limit or a thermal limit. It will just be part of what you need to do when you design a grid system. So I think in order to sort of summarize this chicken and egg thing, I mean, this clear government targets for us in the UK has been phenomenal because it's given that clear direction as to the direction of travel where we need to go. Therefore, it gives us as a system operator the challenge to sort of say, this is where we're going. What are you going to do to manage it? It also gives the OEMs and the market that certainty that this is going to happen. We are not going to have a renewable system, a zero carbon system. Therefore, you've got to get on with it. We've put out the clear analysis that shows the decline in inertia and short circuit in-feed, which again is allowing the market and the OEMs to see that it's coming. Therefore, it's going to be an ever-growing market, and therefore there's revenue for them to do that. So creating those markets and those revenue streams at the moment, because it's very nascent, we are giving these 6 or 10-year contracts to give that investment certainty. We are looking very soon to move that to a much more monthly, daily, weekly type of product. So that if you have a grid forming inverter, you can bid into a daily market, just as we do with frequency response. We've worked with OEMs and continue to work with OEMs as they want to understand what it means technically, what the system is going, what does it need technically, and therefore they can work out how to meet that need. And then finally, once you've done all that, you can put it into the grid code. But I think the key important driver here is that these solutions are zero carbon solutions. These solutions are lower cost than the alternative, because as John said before the break, with 40, 50 gigawatts of offshore wind, it's going to be providing a lot of the power requirements for the northeast of America. If you don't have these products and these services, your alternative is you constrain off some of that 40 gigs of wind you've just built in order to continue to run gas, because you need the gas to provide you that inertia and that short circuit in-feed in that region. So I think, certainly in GB, we are moving at pace because this wall of renewables is coming towards us. We've had 86% zero carbon generation so far on our system. We know what the last 14%, why we purchased that in the market. We know why we bought it, whether it's for voltage management, frequency response, short circuit in-feed or inertia. And what these products are doing now is they're stripping out that 14%. So the next time it'll be 88%, then it'll be 80, and then it'll be 90, then 95. And then by 2025, it'll be 100% zero carbon operation for a few hours at least anyway. So thank you for listening.
Fantastic. Thanks, Julian. I think the plan here is that we'll have all three speakers go, and then we'll have a half hour or so for questions at the end. So thanks again, Julian, and I'd like to go ahead and introduce Dustin Howard. So Brian, you can pull up Dustin's slides. So Dustin is going to talk about some very exciting design and demonstration tests on the grid forming for Type 3 wind turbines. Dustin's technical director at GE Energy Consulting, my old shop. He's been there since 2013, and his expertise in EMT modeling, converter controls, complex control interactions in weak grids and series compensated grids. And quite honestly, what those words undersell Dustin's expertise. He is really one of the tops in the industry on this. And he is now leading technology developments on grid forming, using his PhD from Georgia Tech in electrical engineering. So Dustin, welcome aboard, and take it away.
Yeah, thank you, Nick. Are we good with sound in the back? Okay, great. Again, thank you, Nick, and thank you everyone for your attention. Very excited to present some of this work that we've been doing at GE, really working towards developing some of the products that we think are going to help facilitate the energy transition that we've been discussing here over past couple of days. This work is really the culmination of a couple of years effort that started with an effort towards developing those core grid forming control algorithms. And really over the past, I'd say 6 months or so, through a collaboration with NREL that Vahan presented on earlier, we've actually taken some of those core algorithms that were developed and actually tested them on a commercially available or components of a commercially available wind turbine. So I'll be discussing some of those results from the prototype tests, as well as a few other insights and learnings from that activity. Just to give a summary of what I'll be discussing today, I'll start off sort of discussing the capabilities of wind turbines to provide these grid forming capabilities and sort of discuss that more broadly, and also talk about different categories of grid forming capabilities. And then I'll go into more details about the test bench that we're using to test these grid forming capabilities at NREL. And then really I want to dive into some of the results that we've obtained through those the test and talk about some of the important performance, grid forming performance aspects that we've seen from those tests. And then I'll discuss some of the next steps of this effort and some conclusions. So what can wind turbines do in terms of grid forming capability? I think as engineers, several items come to mind when we think of grid forming. So that may include a resource that can behave as a voltage source behind a reactance, a resource that's capable of supplying phase jump power or synchronizing power, maybe inertial power, frequency droop, black start capability, and operating as a standalone power source, or in a short circuit ratio equals 0 scenario. But I'd like to divide up those capabilities into two broader categories. So the first 4 on the list I want to sort of define as core grid forming capability. So this is really the ability of a grid forming resource to emulate some of the physical characteristics of a synchronous machine. And I want to distinguish that from what I'm calling advanced grid forming capability, which is reflecting, I would say, the more extreme versions of grid forming applications, which includes black start or relatively specialized applications where grid forming can be used and is beneficial. Now, starting on the columns, I've divided wind turbines into 3 different categories here: grid following wind turbines, grid forming wind turbines, and then finally on the right, we have a grid forming wind turbine plus some additional equipment. So this may include balance of plant equipment that may be comprised of energy storage or a diesel generator or extra components within the wind turbine itself. So in terms of the capabilities of each of these 3 categories to meet the grid forming capabilities, sort of starting on the far right here, we expect that all of these capabilities can be met if we have the grid forming wind turbine plus this additional hardware. But what I really want to focus on is the middle column, which is what grid forming capabilities can be extracted from these systems only through software changes. So taking hardware from commercially available turbines, updating the control algorithms, and understanding what grid forming capabilities can be extracted. And this is particularly important for both the existing fleet of wind turbines that are already in the ground and operating, but also keeping costs low for new installations. So the test campaign and what I'll be talking about today is really focusing on the capabilities of these quote unquote off-the-shelf wind turbines at supplying some of these grid forming capabilities. So jumping into what has been tested, I think Vahan gave a nice overview of this. This is a slightly different view showing the type 3 grid forming wind turbine test bench at NREL. I'm showing a 1-line diagram here. On the left, we have a CGI or a controllable voltage source. On the right, we have our wind turbine, which is driven by a dynamometer. So in other words, it's acting like our wind turbine and driving the speed of the generator. And we're really looking at, through the CGI, applying various grid events, both small grid events and relatively severe grid events, and looking at the response of the wind turbine. The wind turbine itself is a 2.5 megawatt unit with off-the-shelf components. for a commercially available turbine today. As I mentioned, the converter controls have been upgraded in the system to reflect grid forming algorithms. But one thing I want to mention here is that this was not simply taking this hardware, updating a few lines of code and sort of pushing the go button on the tests. As I said, this was more than a 2-year effort in not only implementing the core algorithms that emulate synchronous machines, but a good bit of our effort is really coordinating those algorithms in such a way that we avoid overloading the equipment itself, so operating within the limitations of the equipment. So I had a college professor that told us that as engineers, we're going to spend maybe 99% of our time worrying about and designing towards events that happen less than 1% of the time. And this, of course, is it goes along with the same story. What's really nice about this lab environment is that we can, because we have a fully controllable voltage source, we're able to test both relatively small grid events and relatively severe grid events that we can't otherwise test in the field. So jumping straight into some of the results that we've obtained, starting with the phase jump response. Shown on the top right-hand side of this slide, I'm showing the active power response of the wind turbine to 2 sequential phase jumps on the grid. What's really important about this result is the change in the very fast and large change in active power in response to those phase jump events. So this is demonstrating similar capability that a synchronous machine would provide. So the control algorithms were designed to provide this phase jump power response, but also constrain that response within the limitations of the equipment. And sort of to illustrate the key difference here that we're seeing with the grid forming system, I'm showing a simulation result at the bottom right-hand part of this slide. And this is comparing, for the same event, the difference between a grid forming system and a grid following system. And as you can see, the grid following system sort of has a very relatively negligible response to that phase jump, whereas the grid forming system has the large change in power. A couple of important notes on phase jump power. So it does vary. The amount of phase jump power that you can get out of this system does vary based on initial conditions. So what is the operating point you're starting from? Of course, the phase jump magnitude itself. And in addition to that, the phase jump response may be asymmetric based on those initial conditions. Jumping now to another event here, I'm showing the response of the system to a grid frequency drift. So specifically, this is the response, again, focusing on the top right-hand side of the slide. This is the response in active power out of the turbine in response to grid frequency going from 60 hertz to 61 hertz at 1 hertz per second. Again, the important aspect of this response is that change in active power. So that change in active power is related to both how far you deviate in frequency and how fast you're deviating away from a nominal grid frequency. And again, showing on the bottom right-hand slide, just to illustrate the key difference here, I'm comparing through simulations the difference between a grid following system and a grid forming system. And you can see here that the grid following system is pretty unresponsive to the grid frequency event because it wasn't designed to do that. But you can clearly see the change in active power from the grid forming system. Again, it's important to mention that the controls were designed to provide this response, but also constrain it so that the change in power is not so large that it exceeds the capabilities of the equipment. And there's may be significant variation in the amount of inertial power that can be provided. And so this will depend on several things, including the operating speed of the turbine, the stored kinetic energy within the rotor itself, which is related to the speed squared. And of course, the energy input based on wind, and also the proximity to equipment limits that you're starting from. But again, what I've shown on the past two slides is really showing the phase jump and the Rokoff response that is very much like a synchronous machine, which can effectively shows that these systems can act to increase the system inertia and contribute to increasing system strength, but with an asterisk that we do have to pay attention to these important equipment limits and complex equipment limiting aspects. One other result, and this is the last result that I want to share, is the response to a low voltage ride-through event. This particular result is for a 50% low voltage ride-through. A couple things I'll point out about this result, focusing in on the right side middle plot. You can see that the grid forming system responds by very rapidly injecting reactive power to continue support grid voltage for this event, while also maintaining the current within the limitations of the equipment. A couple of other important aspects of this is that there's no mode switching, and actually by design from this system. So in other words, switching between a grid forming mode and a grid following mode. And this is an intentional by design to avoid toggling between modes that you can sometimes get out of these systems if you're using mode switching. Another important aspect is because we're continue to operate as a grid forming resource in this mode is that the amount of active and reactive current that you get out of the system is different than grid following in the sense that we're not controlling the current per se. So the amount of reactive and active current is more tied to the impedances of the system and the residual voltage in the system itself. But overall, the low voltage ride-through capabilities are relatively similar between grid following and grid forming. But of course, the current dynamics during and after the fault are different as a result of the different control philosophies. So I've shared some of the results we've obtained through this effort fairly recently. I'll offer a few comments on next steps. So we're having some ongoing research as a part of this activity, understanding the impacts to the mechanical components of the wind turbine itself, as well as the mechanical controls of the turbine. And full turbine prototypes are planned for this year. A few concluding remarks. I think as a result of this effort and hopefully that I showed in these slides, I think we see that there's tremendous capability for wind turbines to mitigate some of the key risks with the energy transition, which is related to reducing system inertia and weakening grid. But of course, we have to keep in mind some of these complex equipment limiting aspects that include both electrical and mechanical constraints. One final comment related to grid requirements. We think the grid requirements that are upcoming should consider both the existing resource capability, so turbines already in the ground, as well as the new resources that will be coming on in the future, so that we don't limit access to markets. And this really goes back to the distinguishing between those core grid forming capabilities versus advanced grid forming capabilities. And we see that if we think about it in those terms, higher levels of grid forming penetration can be achieved more quickly, making those distinctions. And I will stop there. Thank you for your time.
That's super. Thanks, Dustin. Bet everybody's jumping out of their skins to ask you questions. But before we do that, I'd like to welcome our third speaker who's remote. And I want everybody in the room to appreciate how really late and stalwart Cornelius has been. He's well past midnight. And by all rights, he should at least have a drink in his hand. So Cornelius joined 50 Hertz Transmission in 2016 as part of the medium-term planning team and system operation. He's received his BS and MS in industrial engineering from BTU Cottbus University, respectively. And in 2020, he's assumed the position leader as team leader for large projects and stability analysis in the grid development department. This focused mainly on system planning of DC and offshore connections. So he's got some very exciting material to share with us. And Cornelius, welcome.
Thank you very much for the introduction, Nick, and I hope you can see my screen and also you can hear me well.
Yeah, perfect.
All right. So today I'm going to walk you through our view on our requirements for HVDC and STATCOM. And this involves our motivation, our grid forming understanding, the German guideline on grid forming behavior of HVDC, and finally an outlook. Just to give you an overview, I'm part of 50 Hertz, which is the transmission system operator for the eastern part of Germany and Hamburg. And we are part of a European group of transmission system operators together with Elia Transmission Belgium. And as you might know, Germany is part of the interconnected European grid spanning from Portugal to Ukraine since last week. And thus the whole backdrop is a little bit different to what we've seen in Julian's presentation. But some parts are the same as in Julian's presentation. And just to give you an idea of what's happening in Germany right now, I have just taken the figures for the power generation and demand in Germany from last Saturday. And you can see we have quite a significant share already of PV and wind, which was able to about 60–70% provision of the load. But what would this day look in the future? Like 10 years from now, we would see a picture, probably something like this. And in this phase, we will see inverter-based resources making up over 96% of the whole generation. Yes, this is only for Germany, and Germany will still be part of the interconnected system, but it's going to be stressful in times, I would say. And what does it mean for 50 Hertz? So we at 50 Hertz, we have a strategy. Now we have a share of 60% renewable energy sources of the end demand. And in 2032, we want to be at 100%. And this means that we need to ramp up the installation of renewable energy sources by a lot, at least double the installed capacity in the next 10 years. But in the same time, we're going to phase out of coal, we're going to phase out of nuclear, and we're only going to build up some gas capacities. So we're losing a lot of system services from conventional power plants. And this will lead to definitely increasing cost for stability-related redispatch, when we need to get these gas power plants in the market, although they wouldn't be feasible to operate in certain times. In Germany, we're going to, we have a problem that we have a lot of generation in our control area, which is in the northeastern part of Germany, and we want to push it all the way to the west and to the south. And thus, within the next 10 years, we're going to build up 10 GVA of HVDC converters, which are indicated in the squares on the map on the left side. And to stabilize the grid even further, we're going to build up over 4 GVA of STATCOM. And the dark red STATCOM that you see here will be so-called conventional STATCOM. They will already use grid forming controls, but in contrast to the orange marked STATCOM, they won't have any additional inertia storage. The huge problem that we see now is in some parts of our grid, the equivalent short circuit ratio will be below 1.5 in normal conditions already. So when it comes to outage conditions, it will drop dramatically even further. To give you an understanding of what we think the distinguish between grid following behavior and grid forming behavior is, I've included these two next slides. And you can see the time is marked on the y-axis here. We have the instantaneous time frame, 1 millisecond to 20 milliseconds, and up to 1 second. And we already know how this behaves. I think you might have talked about this today quite often already. So we have the voltage regulation, which takes place quite late. And we have the frequency regulation with the frequency sensitivity modes and so on, which is also quite slow. And in between, we have the voltage stabilization with active damping, internal voltage regulations for the DC components. And then what we've seen in Dustin's presentation as well, we have this really, really short instantaneous reaction in grid following behavior. So this amplitude that we are looking for of the voltage source behavior in voltage stabilization. And finally, the same really, really tiny bit of reaction, the angle part of the voltage source behavior will stabilize the frequency. And then we have the synthetic inertia and speed control as later components. So as you can see here, there's a huge gap between this tiny, tiny first reaction and active damping and synthetic inertia. And in our analysis, it has been shown that we will see stability issues in systems where we have grid following shares greater than 60%. So we need to fill this gap somehow. And this is what we try to do with grid forming behavior. As you can see here now, our idea of grid forming behavior is to have this really early reaction stretched until 20 milliseconds, or as probably as far as you can go, so that you don't have to switch between modes, you don't have any bumps in between. And this can only be done by grid forming behavior. And now this first reaction here would then really mimic what voltage source behind an impedance would look like. And just to compare it, in our view, to synchronous machines, this whole part here, so going to 1 second probably, including the synthetic inertia, would be a comparison to the synchronous machine that we already know. So this really would be the inertia we know from synchronous machine. So we know what grid forming might be. We already know the different aspects of it. It has also been some publications from the European transmission system operator community, where we have the general requirements. But now we need to translate these general requirements into something we can actually specify in our tenderings when we tender our STATCOM, when we tender our HVDC. And this is what we try to do with the so-called VDE FNN guideline, where we try to have a framework for the specifications and the conformity. What we don't want to do is dictate on how you have to build your control, but we just want to assess the desired behavior. And just to give you an overview, I've included the next few slides. So basically the test network, which you can see here, is already quite similar to what we've also seen in Dustin's presentation. And what really is of interest, obviously, is the device under test right here. And all of this part on the left side is basically just the grid side, where you can change the frequency, you can change some voltage angle jumps, some harmonics. The short circuit ratio can be changed via this. And then with this test network, we can include several test cases. And I'm not going to walk through all of them because I guess you've already heard all of them today, but I've marked those that are of the most interest for us. So phase angle jump, the Rokov problem, voltage magnitude steps, the change in network impedance, and finally islanding with voltage source under grid-forming control. And I've included this last part because this is quite interesting. So far, we as 50 Hertz have already tested grid restoration plans based on VSC HVDCs, which have already worked. But back then, it was a so-called a weak grid mode, and it worked perfectly fine. But when going from weak grid mode to the normal operation, we had a few bumps in the system. So this is something we don't want to see in grid forming controls. The whole idea behind this is that we can use the whole network, the whole set of test cases here from our first specifications for tendering, for the software in the loop test, for engineering studies, for control hardware in the loop tests, and finally conformity tests. And this is this makes it so attractive for us. Looking at an example now. So what we did here when we specified the last tender for a 2 gigawatt HVDC system is we had this test network and we had this device under test. And in order to know how it should behave, we needed to come up with a generic MMC VSC model. And with this generic MMC VSC model, which we know is grid forming, we are going to produce this reference curve, which is marked in green here. And as you can see here, in this case, test case, the device was loaded with 50%, and we had a phase angle jump of 10 degrees. And what we want to see is the first inherent reaction, which you see perfectly here. We want to see a maximum reaction, in this case, after 30 milliseconds. And we want to return to the initial value after 500 milliseconds. We want to see a well-damped behavior. And since we're talking about HVDC, we don't want to see the same behavior on the opposite station. So the opposite stations should really have a smooth reaction to this event on station 1. So this is what we create as a TSO, and then we have this in our specifications for the tendering. And during the tender process, all the manufacturers have to run their simulations with their models, with the same test cases, the same test network, and then they will have their real behavior handed over to us as well. And once these envelope curves that are marked in orange dotted lines here are violated, then we have to discuss. And as you can see here, these envelope curves, they're a lot more tolerant in the direction that we want to have the correct reaction, and they're really strict on the other end. So finally, for an outlook, where do we go from here? Is this already where we want to be? Obviously not. There are quite a lot of open questions. How do we implement converter current limits in this generic models that we need to use in order to specify our HVDCs in STATCOM? How do we consider energy storage correctly, especially for STATCOM, we don't use any storage devices. So this first phase of STATCOM that we are going to build up at 50 Hertz. How will we determine systemic grid forming control needs? So we know that we are going to build basically all of our devices grid forming, since we know there's a lag, but is there some way to optimize it in the long run? And final question is, what is the minimal energy storage that we need to have in order for a device to identify as grid forming control? To tackle these steps, to tackle these questions, and to implement even further grid forming requirements, We will amend the requirements for generators code of the European transmission system operators within the next few years in order to not only have the TSO assets as grid forming control, but also all energy generation units. Furthermore, obviously, now that we have tendered our HVDCs and STATCOMs, now we need to review the manufacturer tender documents in order to see what they've done and how they can comply with our specifications. And then finally, coming the year 2025, we can finally observe the real life behavior, how the assets actually react on the grid. But I think the path is pretty clear that at least for us, for 50 Hertz, we are looking at 100% grid forming converters in all new installations that we're going to do ourselves. Thank you very much for your attention.